Your next phone may run AI models that today still live in massive data centers. In 10 years, billions of edge devices like phones, cars, wearable, even factories could become tiny data centers themselves. The question isn't if this happens, but how far it goes. And who wins when the balance of AI shifts from the cloud to the edge? When people say edge AI, they usually mean running inference directly on devices. The cloud still does the heavy lifting for training massive models, but inference, the part where a model makes predictions, can increasingly happen on the edge. Examples are already here. Apple's neural engine powers on-device Siri and Face ID. Qualcomm's Snapdragon NPUs run stable diffusion on Android phones. Tesla built custom inference chips for its cars. The difference from cloud inference? Latency drops from hundreds of milliseconds to nearly instant. Privacy improves when your data never leaves the device. And cost? Serving millions of inferences in the cloud racks up huge bills. Edge inference avoid much of that. So why is Edge AI suddenly possible? The short answer: chips got smarter, models got leaner, and the software got easier. Let's start with the chips. Most devices already have CPUs, the general purpose processor that handles everything from running your apps to managing your files. CPUs are flexible but not very efficient for AI because they process one instruction at a time. GPUs change that. They can process thousands of operations in parallel, which makes them perfect for training big AI models. But GPUs are still heavy. They use a lot of power, take up space, and are ideal for small battery powered devices. That's where NPUs, neural processing unit, come in. Unlike CPUs and GPUs, NPUs are built from the ground to accelerate matrix multiplications and tensor operations, the core math behind neural networks. They are optimized for lower precision arithmetic, which AI model can tolerate, and they use less energy for the same workload. In simple terms, CPUs are flexible but slow, GPUs are powerful but power hungry, and NPUs are specialized, efficient, and perfect for running AI on your phone or car without draining the battery. Now let's talk about the models. AI models are usually huge, billions of parameters that strain memory and compute. To shrink them for the edge, engineers use techniques like quantization and sparsity. Quantization means reducing precision. Instead of storing numbers with 32 bits in detail, you use 8 bits or even 4. It's like seeing a photo in lower resolution. It loses some sharpness, but it still works for most tasks. Sparsity means pruning away the parts of the model that don't contribute much. Imagine a neural network where many connections barely change the outcome. You can cut those and the model still works but runs faster. Do these shortcuts hurt accuracy? A little. But in practice, the drop is small compared to the massive gains in speed and efficiency. And for real world tasks, like unlocking your phone with Face ID or transcribing speech on the fly, it's still more than good enough. Finally, the software layer made it usable. Frameworks like TensorFlow Lite, CoreML, and ONNX have become the bridges between research models and consumer devices. TensorFlow Lite is Google's lightweight toolkit designed to deploy AI models on Android phones, IoT devices, and even microcontrollers. CoreML is Apple's equivalent, but directly into iOS and macOS, optimized for the Apple Neural Engine. ONNX is an open standard, a kind of a universal adapter that lets you move models between frameworks and run them almost anywhere. Together, they mean developers no longer need to be hardware expert to put AI into your phone or your car. The toolkits handles the heavy lifting. And here's where usability matters most. Running AI on the edge doesn't just save money for companies, it makes everyday tech better for people. It means your phone can recognize your voice instantly without sending recordings to the cloud. It means a self driving car can react in milliseconds without waiting for a signal. It means health monitors can detect issues even when you're offline. In short, Edge AI isn't just an engineering trick. It's the difference between AI that feels clunky and AI that feels invisible, fast, private, and reliable. Fast forward to 10 years, edge devices could run models that feel impossible today. Not necessarily trillion parameter giants, but smart ensembles of compact models optimized for speed, memory, and real time interaction. Scale matters. Today, 2025, there are already 15 billion plus edge devices in use worldwide, phones, sensors, IoT devices, etc. Some forecast place edge-enabled IoT devices at around 5.1 billion just by 2025. By 2035, the edge AI market, hardware, software, and services, is projected to grow from around 24 billion US dollars in 2025 to around 360 billion US dollars. That implies tremendous expansion in the number and capability of devices doing AI on the edge. So it's reasonable to imagine 10 billion plus edge AI capable devices by 2035 or even more, especially as more smart devices upgrade. That fleet size would far outnumber the number of centralized data centers. Rather than killing the cloud, this shift rebalances it. The cloud trains, orchestrates, and updates. The edge runs sensors and act in real time. Now the limits. Memory is the first wall. Even compact models smash into RAM ceilings, and bandwidth is often the real choke. Thermals and battery comes next. Sustained on-device inference can overheat a phone or drain a wearable fast. Fragmentation doesn't help. One model, a thousand device variants with OS differences, NPU quirks, drivers, and security policies to navigate. And remember, privacy isn't the same as security. Keeping data on device doesn't magically make the endpoint safe. There are exciting wildcards. Neurformix chips promise brain-like efficiency for spiky workloads. Optical and photonic accelerators move data with light to cut latency and heat. Federated learning lets devices learn locally and share only gradients. And new memory and packaging like LPDDR6, stacked SRAM, chiplets, 3D integration attack the bandwidth problem head on. If you are scanning for durable value, look for teams work on memory bandwidth, thermal design, model compression, and safe rollout. Those are the true blockers. Whether you are investing or building, that's where the hard problems and the lasting moats live. How do you know the edge shift is actually happening? Watch annual shipments of NPU equipped devices and, crucially, the tops per watt they advertise. Track which OS level features quietly move from the cloud to on device, such as speech, vision, translation, photo tools. Pay attention to toolchains updates that makes 4 and 8-bit quantization, sparsity, and one-click deployment standards. Compare thermal and battery benchmarks for on-device AI tasks in flagship phones and cars. Look for enterprise case studies showing real fleet orchestration, stage rollout, safe rollback, A/B testing at the edge. And finally, not any regulatory guidance around on-device AI safety and privacy. Those are the breadcrumbs. If Edge AI really scales, who actually captures the value? And how could a tech-minded viewer think about the exposure? Start at the bottom with silicon. The story here is efficiency. More tops per watt, better on-device memory bandwidth, tighter hooks into software. A couple of names to watch. Halo, which just means it's Halo 10H Edge Accelerator, generally available with on-device generative AI support. And SIMAI, building a software-centric ML SOC aimed at pushing vision to transformers to multimodal Gen AI on the edge. Both signal that serious inference is leaving the data center and landing into small boxes. Above the chips live the toolchains and runtimes. The translators that slim big research models into battery-friendly, hardware-aware builds. Watch Edge Impulse, widely used to train or port tiny and embedded models, and Latent AI, LEIP, a platform that automates quantization or compilation of reports large compressed without breaking accuracy wins. If deployment feels one click and portable across devices, it's usually because this layer did the hard work. Then come the platform OS, iOS, Android, automotive and industrial stacks. Control the OS, control the APIs and defaults, that's the mode. But the real magic shows up when you try to run this at scale, which brings us to orchestration. Keep an eye on the Memfold story. Recently acquired by Nordic Semiconductor to offer chip-to-cloud observability and OTA rollouts. And on field looks like vertical platforms such as VM for deploying and updating AI across a lot of devices. Owning the fleet and update channel is real power. At the application edge, you'll see category specialists proving value where latency and privacy are non-negotiable. A crisp example is seeing machines. Driver monitoring AI running in vehicle, now adding non-drowsy impairment detection. Exactly the sort of things you can round trip to the cloud. And then there are wildcards, bets that could bend the curve on power and heat. Synsense and BrainChip are pushing neuromorphic event-driven chips for milliwatt class always-on sensing. Light Matter and AI Labs are attacking data moment bottlenecks with photonics and optical I/O. If even a part of that sticks, the edge budget of AI gets a lot bigger. So, in plain English, infrastructure and integration usually outlast single labs. If you are curious about exposure, look for players that control adjacent layers, silicon plus software, or platform plus distribution, and pressure test them against the hardware problems we covered: memory bandwidth, thermals, fragmentation, and safe rollout. And this is educational context only, not financial advice. Do your own research. For founders, go where the pain is acute. HMLOps is still immature. Model compression, profiling, feed rollouts, and safe rollback receive a single clean workflow. Privacy preserving analytics at the edge, on device summarization with minimal telemetry will help regulated industries adapt faster. Energy aware runtimes that hit latency, SLAs while minimizing heat and battery are a clear need. Verification and safety tools that catch bad edge behaviors before a wide release could save companies real money and reputational risk. Vertical offline first user experiences, health diagnostics, vehicle intelligence, factory inspection, retail loss prevention are ripe for focused products. An curated marketplace of small hardware-aware models with clear packaging and licensing would accelerate the whole ecosystem. Pick a niche where latency, privacy, or connectivity make edge a must-have, not a nice-to-have. Zooming out to 2035, here's a quick context score: 0 to 5 on each. Readiness is a 4. Cost momentum also 4. Infrastructure sits on 3. Regulation is early at 2. Capital intensity is a 3. Moats look like 4. Substitution risk is a 3. Public market exposure is a 3. Total 26 out of 40. Accelerating, not mature. There's plenty of upside for picks and shovels and for integrators. Apps win in the corners where latency and privacy are non-negotiable. I'm just sharing frameworks and exposure classes so you can do your own research. And if you're building, so you can choose hard problems that really matter. Comment down below what you think about this course. In 10 years, billions of edge devices will be smart AI data centers in your pocket, your car, and your home. The cloud won't vanish, it will train and coordinate, but the edge will matter more than ever.